I think it's really cool that we heard kind of three talks today that are potentially very different temporal kind of scales of brain activity. We saw working memory scale, we saw auditory processing scale, and we all the way down to oscillations scale. So this is very exciting. I'll open up the floor really quickly just for, well, for discussion, any points that people want to bring up, but especially if you have questions for any of the speakers. There have already been a few in the chats. I will try to get to them, but if anyone has them at the moment, feel free. Okay, I'll start with the chat ones.
I have a question, Andre, if I can.
Yeah.
Yep.
Hi, Floris.
Hi, Andre. Yeah. So I had a question for you.
Yes.
If that's okay. So my question is, because I was curious about the gamma findings that you present. So because the range of the gamma band frequency that you select, like from 50 to 150 hertz, right? So it seems really broad. And it made me think of this biophysical model by Kai Miller that suggests that if you take this really broadband gamma band signals, that they might sort of be a spectral reflection of spiking activity. Now, and I would expect that basically all neurons spike, right? So in that sense, you might then be surprised that it would have a sort of a bias towards the superficial layers. So my question would maybe be like, do you think that there's more spiking activity in superficial layers? Or is it maybe at certain times that there's more spiking activity in superficial layers, or maybe you sample more of those? Yeah, I was wondering if you could relate it to that.
Yeah, that's really interesting. So neither one of those things are true, incredibly, believe it or not. So we did quantify that in my 2018 PNAS paper. We quantified how often we see neurons, and we see them more often in slightly deeper layers. It's not a huge effect, so we see them very often, of course, in superficial layers, but just a little more often in deep layers. And also the resting state spiking activity is slightly larger in deeper layers than superficial layers. So both of those findings sort of suggest that a simple Kai-Miller type model probably doesn't account for our results. But then the question is, well, what does account for the results? And it could be that there's a lot of synaptic inputs coming into the superficial layers, because there, as you said in your talk, you have both, feed forward inputs and feedback inputs. There's the layer 1, there's lots of the dendritic arbors of both superficial and deep cells have massive dendritic arbors in the superficial layers. So all of that points to perhaps more total synaptic activity happening in superficial layers, which could generate that gamma signal that I'm talking about. So the gamma signal that I was showing is a mixture between true oscillations and this sort of spectral, high frequency spectral envelope activity.
Mm-hmm. Okay, yeah, that's really interesting. Yeah, and if you would just look at the band limited gamma, would it change the picture, you think, or?
I haven't done that yet, but other work would suggest that it's also superficial and middle layer centric, the actual oscillatory component of the gamma band. So I don't think it would change the picture dramatically. And these oscillations, they are not as present in higher order cortex as they are in lower order cortex, in the gamma range specifically. So gamma is a little bit stronger in visual cortex. We also quantified that recently looking at bursts. So what percentage of the time is the LFP in a truly oscillatory state? And we found that those bursts occur a little bit less often, and interestingly, at a higher frequency, the higher you go up into the cortical hierarchy. So they occur with a longer duration and a shorter, a longer duration and a lower frequency in visual cortex compared to prefrontal cortex. So we definitely see these little oscillatory bursts, and they are also in predominantly in superficial layers.
Yeah, thanks.
Mm-hmm. I had a question for you, Floris.
Yeah, sure.
So it's very inspiring and beautiful work. Thanks for that talk. And I was wondering if some of those initial studies that you did also with Peter looked at attention versus prediction, being modulated like that. And so do you think if you would do that type of task, you would actually see the shift from deep to superficial layers? Is that something that maybe we can take that offline as well, because I've also been thinking of a animal-based style attention versus prediction task, but I just wanted to get your views on whether you think the predominant layer would shift in that type of activity.
No, that's a really interesting question. So I must say that I think it's notoriously difficult to try to isolate those signals, because if you have some predictability in the environment, then your attentional signal system will often use that predictability, right? Like in the classical Posner type of task. So in that sense, it's not very easy, I think, to really cleanly separate them, or at least to look at their interaction is pretty tricky. But it's an interesting question. Yeah, I think indeed you would, based on the findings we have collected so far, expect that you would get a shift from deep to superficial. So if you have particular ideas on paradigms that might achieve that, I would love to hear about it. So
okay, I do have an idea for a paradigm, so I'll send you an email to follow up.
Great, thanks. Yeah,
thanks.
Looking forward.
Okay,
That's great to hear. We want this type of event to make collaborations. It's a really nice thing. Are there any other questions from others? Jeff has his hand up as now.
It's actually a little bit inspired by Michelle, but I think it's potentially a general question, and that is, how important do you think it is to use natural stimuli versus sort of classical simplistic or perhaps more fundamental stimuli? And I mean, it's motivated by discussions that a lot of people are having about context and sort of difficult to understand things. I'm in the auditory regime. It's very clear that there's some advantages to using natural sounds, but then you have a task, for instance, that is potentially unnatural, right? About like focusing in on frequencies. And so I guess a general point is whether we think when you're in sensory systems, it actually really matters what you use in revealing laminar patterns and activity processing.
Yeah, I like that topic very much to discuss, but I don't have a straightforward answer to it. What I can, from auditory systems, say that for sure there is a lot of work showing that actually especially if you go to higher level auditory cortex, but already in primary regions, you get neurons whose response is not predictive, or whose response to combined features is not predictive based on the response to those features presented alone, right? So I think there is a difference. We definitely get much more drive from natural sounds compared to the artificial sounds. So I think for me that puts preference on the natural stimulation. Perhaps it is also important to keep in mind that auditory system may be different than visual system, in a sense that we have an auditory system a lot more subcortical processing going on, right? So there are it may be that primary auditory cortex hierarchically is actually higher level compared to primary visual cortex. So there may be a difference there to keep in mind as well.
Yeah, so I would add that actually, I think when people looked at it in the visual system, the responses are much sparser actually for natural stimuli compared to these kind of more unnatural stimuli that we often use. But I think I would be surprised if the system works really or completely differently depending on the type of stimuli that you throw at it, especially for early visual areas. But you're absolutely right that context plays a big role, and it's often kind of taken out of the equation in these unnaturalistic situations. So that's why, but I think you can actually study context also in unnaturalistic situations by be it sort of manipulating spatial or temporal context without completely giving up on experimental control. So I think I have not seen any study really that suggests that the brain works completely differently when you throw naturalistic stimuli at it compared to simple ones. So I think it's true we need to also consider that complexity, particularly to look at context effects, but you can, I think, also do this in a well-controlled setting. So.
Bianca, you also had a question?
Yes, that's right. I think my question is primarily for Floris, but I think might also be related to Michelle's work. So that is a more general question about how predictions affect our perception and neural processing. And with that, I'm really referring more to this to these effects that we see in the literature, that some studies really follow this Bayesian idea that predictions enhance our perception, they really bias our perception, but then others say that our predictions basically suppress neural activity because it's not really relevant. And I guess there's several things that could be going on here. So of course it could be that it just depends on context, as you also mentioned. Maybe it's depending on whether you need this information for the task versus I'm just passively observing and it's not interesting. Or it could be related to different analysis methods, where maybe if we look at the bold amplitude, we see suppression, but if we look at decoding results, we see sharpening, for example. Or indeed, as Michelle also mentioned, that there's maybe different experimental designs that play a role. So I was just wondering what your take is on this very general question.
Yeah, my take on it is that indeed it's complicated. I think would be the really, but as you already say yourself, so I think it sometimes depends on the level of analysis that you look at. So that at the level of maybe a whole area, you see one thing, but if you zoom in, yeah, you might see sharpening in some neurons, or you see a sort of a sparser representation. I think when we look at time domain data, we sometimes also see that the neural response is just temporarily truncated, which if you look at bold signals that aggregate over time would look like a reduction or maybe a dampening of the representation, but it could just mean sort of like a more efficient representation that basically then goes back to baseline more quickly. And that is also something that you would anticipate from models of recurrence processing, right? Because then if there is like more sort of recurrence, if the recurrent signal basically matches the incoming signal, you will basically reach a steady state point more quickly. So I think the lens through which you look at the effect will sometimes determine what kind of pattern you will observe. Yeah, I thought indeed that Michelle's talk was a really great example of that, where she saw that it also really depends on the distance from how the attention effect behaves. Yeah.
And then additionally, I guess still the method, right? So if we're looking at bold, who knows what we're actually looking at, right? And of course, electrophysiology, the studies that are there, at least in the auditory system, they definitely are not sampling all regions, all neurons, right? So they also there's a big selection going on. So that may even further complicate all of the aspects that you both already mentioned. Yeah, in that sense, I think perhaps the modeling with coupled with biophysical models could help bringing these modalities a bit closer to each other.
Yeah, I guess it is neat, as you say, it really depends on what you focus on, right? If you maybe just focus on attention, you see a certain effect, but then if you focus more on this prediction, it's a different effect, or the way you analyze it. So it really makes a very, very complicated picture. So I guess it's really would be interesting to combine different methods with different paradigms to get more idea what's really going on.
Yeah, and I think there the modeling really can also merge results from different, make very specific predictions that could go across different methods, that could go across different species, and actually allow us to say, okay, this result is in accordance with the result of that other study, where now we're kind of just being a bit hand wavy, saying, yeah, probably it's the same thing, or maybe it's a different thing. But it would be nice to really have something that could merge these, a model that could merge these things, I think, these results.
Thanks.
Renzo, you had a question as well?
Yes, also maybe directed to Michelle and Floris. The first two dinners were more about the the MRI part, the fMRI, what the signal means, how to acquire it. And also I think that the field of layer fMRI in general has shifted over the last years quite a bit from this methodological focus to kind of the neuroscience or cognitive neuroscience focus. And you are, I would place you more on the latter, I guess. And so I was wondering, considering that there are a lot of method developers in the audience, what are the things that annoy you most about doing layer fMRI? What is your wish list of things that people should continue focus on to make your research easier?
Well, I think, Renzo, you are working on one of them, right? VASO for auditory applications, I think would be a very interesting thing for me.
Yeah, for me, I'm annoyed, of course, by the SNR, which is very low. I'm annoyed by the draining veins that you get this depth bias. I'm annoyed by the slow TR. I'm annoyed by a lot of things, but I think they are, all of them are, yeah, hopefully going to be addressed. Yeah, maybe VASO will, I mean, I think VASO has more potential for specificity and for sensitivity, at least as far as I understood it. So if we could get sort of like a high SNR signal, which is, yeah, that would be wonderful. Yeah.
Maybe as a follow-up, do you think we have enough resolution there? Or like the models that you show kind of match the resolution that we are just at the edge of seeing there? So it's more SNR and the training veins, I take it. It's not really the resolution that limits you too much.
Yeah, and if you go, if you have a sufficient SNR, sufficient, and basically using contrast that does not show you, does not have the bias to draining veins, it's the coverage that is a problem. So that is another thing. When we use the 3D Grace for the evaluating cortical dependent stability, we saw beautifully unbiased signals and preferences basically, but we were only able to get both hemispheres in half of our participants, because in the other half they either moved a little bit and they were out, or they, you know, that coverage is another issue that then comes in. So yeah, I do think, even with all of this, I don't want to be too negative. I do think it's possible, especially if you have highly trained participants that lie very still for a very long amount of time, then that's great, then you can do it. And, you know, we're training the participants, so we have many now coming back, and then it works.
And Renzo, I think with respect to spatial resolution, I do think that it would be great to have higher spatial resolution. I think now we basically always look where, I mean, we're looking for our keys where the light is, right? So I think now we're sort of simplifying and into these three compartments, and it works well at first approximation. But I'm sure that if we would have the resolution to cut it into 6, we would make discoveries, yeah, that we can't at the moment. So.
It's quickly to build on what Renzo was saying about the resolution. Obviously, we're working hard to get like smaller voxels. Obviously, SNR is a problem. Obviously, coverage is a problem. But another big problem, which does not only apply to like more precise voxel, applies also to the current resolution you can achieve, is alignment across runs and across modalities as well. Obviously, when you go to smaller voxel, we're trying to get to 0.5. There's been a couple of people published with 0.6. John showed a really nice demonstration of 0.6 data recently. But then now alignment becomes very, very, very tedious. So as we develop resolution and as we develop acquisition methods and optimize acquisition, we also need to think about post-processing strategies. How to optimize alignment across runs? Obviously, the acquisition times are limited. We cannot keep people in the scanner for a long time. We want to do statistics within subjects. And now aligning run to run becomes really, really tedious. If you think that at 0.8 it's a challenge, then when you get 0.5, 0.6, you're off by like a half, you're off by a voxel, you're off by a layer. And then now your results becomes very difficult to interpret. So that's another, probably, something.
I can't
Renzo,
agree more with that.
Yeah, Renzo, so Dr. Bastos showed in the first lecture neuronal signals that are, on the order of 200 microns, right? When he looked at CSD, and definitely multi-unit activity. So I don't think it's a question. I mean, we do need a much higher resolution, of course, while maintaining signal to noise ratio. All the other items, I think, are doable later on. And of course, with fMRI, as people said, I think, Michelle, you want more coverage, et cetera, et cetera. But for layer fMRI, what you need is high resolution and signal to noise ratio. That's it.
Yeah, well, certainly I found the distinction in this set of lectures compared to like the last time we met very interesting, because the people who develop methodology somewhat arbitrarily divide the cortex into 10 interpolated layers, and I know Renzo does this, we've done it, so I'm not casting stones. But the neuroscientists are settling on 3 layers, it looks like, from today's talks, as a practical reality of point spread function, signal to noise, coverage, etc. And of course, that's really not quite good enough. I mean, if you look at the laminar electrodes, all the laminar electrodes from NeuroNexus or whatever, they're all 100 and 150 microns spaced. So you want that kind of resolution, ideally, if you're going to compare laminar recordings with the neurophysiology and fMRI. And we're a long way from that in humans. So there's still a lot to do, but I mean, I think it's still, I'm optimistic.
But Ravi, to push back a bit on that, I mean, if you look at some of the CSD plots that we saw today, often the attentional effect, for example, or also just the bottom-up effect, I mean, even if you have these laminar probes with lots of context points, these neurophysiologically measured effects have typically quite a spatial profile that looks to me actually well as approximated by like a 3-layer model almost.
But if I can also push against that, Flotis, one step below, the reason for that, I believe, is that let's say you have a probe with 150 micron spacing. Then when you do CSD as a second spatial derivative, now all of a sudden you're integrating over 150 times 4. So it's almost like the method and the resolution, even of those electrodes that that I use and that Peter Roelfsma use, it sort of forces you into a 3-layer model because of the lack of resolution, even at 150 micrometers. So all of our expectations is that as we push forward with an order of magnitude larger signal sampling, that as you were also saying, that we'll be able to pull out more specific effects across potentially 6 layers or sub-layers and things like that. So I think it's still a little bit too early to say that for sure, but at the moment, yeah, it's a relatively good approximation of the data we have, but it may be that we're just at the tip of the iceberg. So I think it's a very exciting time for us as well to be developing these higher spatial resolution methods.
Good point.
Also, to add to what both Professor Menon and obviously Professor Shmuel knows very well, as we go smaller and smaller voxels, can we actually sample more precise hemodynamics, or is there a limit to what we can get at? So, for example, like Professor Shmuel has shown in 2007 that it was, and then like obviously there's been like follow-up studies that when we measure the point spread function of your functional signal versus the point spread of the image versus your nominal resolution, there are some limits and differences. So going smaller and smaller, and also what SNR doesn't necessarily mean we can actually sample neuronal activity in a more precise way. So that's another thing to take into account. And maybe both Professor Menon and Shmuel can comment on that a little bit.
Well, it's certainly true. And there was even a paper very recently, but I think people have been looking at this for at least 20 plus years, that the vascular point spread function of BOLD and possibly even VASO So this is related to biology, essentially. It's not related to the imaging technique, ultimately, may actually be relatively broad. And so you may never be able to recoup down to the 150 micron specificity. There are tricks you can play. So, Amir has done this, Camille Odag has done this, where you try to do some vascular deconvolution based on known network architectures, and that might help reduce the point spread function slightly, but it's still, I would say, an open question. If you could stimulate, and we're trying to do this now with optogenetics, but I don't know the answer yet. If you could stimulate one neuron or a few neurons in one infinitesimally thin layer in the cortex, how big an fMRI, whether it's vaso or bull, doesn't really matter, how broad a vascular response would you get? I think the jury's still out on that.
Yeah, so I agree. Of course, there is a hemodynamic response, point spread function, but I think, with that, I challenge all the MR physicists here. I'm more in the middle, right? I'm evaluating signals, etc., to find the contrasts that are more spatially specific. Of what I've seen, I think that vaso is like encouraging, and of course grace that we have been using. But I'm optimistic, and from where we are, we can only improve. And also, following on what Ravi said, I think that the jury is not out with regard to laminar fMRI point spread function. It's a little bit of a different ballgame, right? Most of the studies on spatial specificity looked at tangential to the surface of cortex, and not necessarily it is the same between layers, especially if we use sophisticated modeling approaches.
Yeah, I think that is a really good point, and on top of even these points, it might be useful for us to think about how many neuronal compartments are even accessible through the type of signals that we are recording. This is something that I've been interested in lately, is trying to understand. We look at Andre's data, and he says you can approximate it roughly with a couple compartments, etc. But of course, if the neuronal scale went finer than that, they may be able to pick up something. And it's important for us to find ways of measuring what things we actually can pick up on from the neuronal side, I think. And I think a lot of people are working along those lines, and it's exciting to see this progress. So we have, I think, lost two of our speakers to daddy duty. But if there are any other questions or discussion points, I think a lot of this is really exciting to hear about. Otherwise, we can continue discussions offline, because I think we saw a little bit of discussion about collaboration across scales already, and that was exciting for me to see. But I think that there are a lot of opportunities within this group to kind of have the ability to talk about totally different aspects of the signals that we're looking at and how they can be integrated and modeled, etc. So, Luca, do you want to continue with an outro of any kind?
Well, just to thank everyone again, and say we're already planning our next meeting, so stay tuned. We already have like a set of speakers, and hopefully we'll be in touch soon with some more exciting talks and discussions.
Yeah, thank you everyone for joining.
Thanks, bye-bye.